Okay, see, if you didn't get your exam, I think I just have one or two of you just come see me afterwards. And just want to give you an update. We're sort of on our exam. We are, we're here on the 13th, so we still have about 7 class days before we get to the exam. Probably not going to need all 7 of those class days. We'll probably have a day out. We haven't had a day out yet. Right now we're going to have a day out, so I'll let y'all know in the next week or so when that'll be. Okay? All right, so let's look at the magnetic force between 2 parallel conductors. Current carrying wire, as we know, creates a magnetic field. Right, if I have a wire with a current through it, it creates a magnetic field into the page on this side, out of the page on this side. We found that magnetic field was it mu naught I over 2 pi r? Was mu naught I over 2 pi r. So at a certain distance from that wire, say if I'm looking here, that's my distance r, I is the current, mu naught is that constant, that 4 pi times 10 to the minus 7. So we can determine what is the magnetic field due to this current carrying wire. When we have another wire that sits inside that field, so say we have another wire right here, it sits inside the magnetic field that is generated by this wire, and so it's going to experience a force, because anytime I have a current carrying wire inside a magnetic field, it'll experience a force. So when another wire is in this field, it experiences a force due to this magnetic field. Both of these wires are going to experience a force. I'll figure here. Yeah, so if I have these 2 wires, the first wire, looking at this wire, it generates a magnetic field into the page, out of the page. Remember, we use our right-hand rule, that second application of the right-hand rule. Let our thumb go in the direction of the current. They go into the page, out of the page. And so you're similarly going to get a magnetic field down here. I'll draw it in blue. That is into the page, out of the page, like that. So your magnetic fields look the same because our currents are in the same direction. But if I think about this whole region over here has a magnetic field that is out of the page. So this red wire up top sits inside that magnetic field. I can determine the direction of that force. I have a magnetic field here. I have a current here. So let's see, my current is like that. My magnetic field is like that. Index finger, magnetic field is out of the page. So my force is downward on this top wire. That's the force on wire 1 due to wire 2. So it's the force on the top wire due to the magnetic field generated by the bottom wire. We can do the same thing for the bottom wire, and we'll find, as you might expect, that the force on wire 2 due to wire 1 is going to be equal but opposite. So this force on wire 1 due to wire 2 will be equal to the current times the length of our wire times the magnetic field that's generated by wire 2. So this is the current in wire 1, and then this is the magnetic field generated by wire 2. Okay? And then similarly, we can go ahead and continue this out, because I know that my B is mu naught I over 2 pi r. So I can say this is I1L times mu naught I2 over r, which is just the distance from the second wire. You'll follow me on this? These 2 wires are separated by a distance r. this wire generates a magnetic field. That magnetic field at this point is equal to mu naught I2 over R. And so my force then is going to be I1, which is the current here, times the length of the wire, times the magnetic field, mu naught I2 over R. And then in a similar way, you can go through the same argument for F12, and you'll find that this is equal to the negative of F21. We can sort of clean it up a little bit. It's going to be equal to, F21. You can further clean this up just a little bit and write it mu naught L I1 I2 over R. Y'all remember with Newton's universal law of gravitation, we had this whole thing with Newton's third law where the forces were equal and opposite, and they came out that way in the equation because we had M1 and M2 were both in the equation. We have a similar thing here. I1 and I2 are both in the equation for different reasons, right? This one is the current, and this is just what's generating the magnetic field, but it works in a similar way, that our forces are going to be the same. And it arises because of that Newton's third law, that anytime I have one force, I have to have an equal but opposite force. Yeah, Cody? Right here? No. Just showing that the magnitudes of these are the same, but they're opposite in direction. So that's what this negative means, that F12 is the negative of F21. See, this is F21 right here. F12 is just the opposite of that. They have equal magnitude. So if they're in opposite directions, do they feel an attractive or a repulsive force? That is, if the currents look like this, do they attract or repel? They do what now? Attract? They repel, right. So up here we had wires that had the current in the same direction. These attracted. So anytime they're in the same direction, they're going to suck together. Anytime they're in opposite directions, they're going to repel from one another. So here my forces will be opposite but the same, opposite in direction, same in magnitude, and they're going to be repulsive forces. So here I'll have a repulsive force. This is how we define the amp. Remember we called the amp a coulomb per second. 1 amp equals 1 coulomb per second. It's actually very difficult to measure the amount of charge moving through a wire. I mean, how the heck are you going to do that? You can't see the charges, right? So you have to sense them in some way. And this is the way we sense them, by the force that they experience. And so this is also the way that we define what is the ampere, that unit for current. And it's defined in this way. It says that if we have 2 long parallel wires and they're 1 meter apart, they carry the same current and they experience a force per unit length given by this, then we say that that current equals 1 amp. All right, so this is the physical standard that we have for an ampere. We have 2 wires that are really long. That means that you don't worry about the end effects. Anytime you have wires, if I have 2 wires here and here, you know, the wires are going to generate magnetic fields that will generally be, what's the word? Homogeneous? They'll be sort of normal. I always get those mixed up. They're going to be basically the same. They'll be regular, I guess, as we look at the magnetic field along the straight parts of the wire. But on the end, you're going to get funky things where the poles come in and they curve around. So that's why we talk about long, parallel, straight wires. And that's all that we'll deal with, are long, parallel, straight wires. All right. Let's look at magnetic fields of current loops. This is very similar, but it has some nice applications. You can use the right-hand rule to determine the magnetic field. So if we have a loop of wire, that has a current going in this direction, like that. It just has a coil, and you put a current through it, just like we did with that, what's it called, the screw, that third application of the right-hand rule. With our thumb going in this direction, it goes into the page and then out of the page. So my magnetic field around this loop of wire is going to be into the page, out of the page, into the page, out of the page. It'll be the same all the way around. You can try your right-hand rule so that all inside this loop, the magnetic field is coming out of the page, and all outside of the loop, it's going into the page. Generally, we're only concerned with the magnetic field inside the loop when we start to apply this, because we use it for switches of certain kinds. This magnetic field, be careful with this, it's mu naught I over 2R. This looks a lot like the magnetic field due to a long straight wire. The only thing is you're lost the pi. Look back on the equation sheet. Just make sure that you're up on that equation sheet and you know what's on it, especially for this next test, because you got a lot of equations on here for different things. But let's see, so here we have our two equations for magnetic field. This is the one for a straight wire, and then this is one for a loop of wire. You can tell the difference. The easiest way to tell the difference is that this one has an N. I'll show you this one for a second, but this is just the number of turns. All right, you need to know your equation sheet, what's on there, and what you'll have for the test. But the good way to tell this apart on the equation sheet is this has N for number of turns, and on the long straight wire, that doesn't really make any sense. Okay. If you haven't yet, I would definitely print out that equation sheet and start looking at it as you work through the homework on the next set, because there's a lot of different things there. Okay, if you have multiple turns of wire, we just multiply this, N times mu naught I over 2R. And the good application for this is a solenoid. It's actually very difficult to create a mechanical switch that operates at a distance without actually touching it. And one of the ways that we do this is with a solenoid switch. It's just a coil of wires, and when a current goes through it, it creates a magnetic field. So you have a coil that looks like this. You send a current through it, and usually you have some mechanical, like some magnet or whatever, that sits inside of it. And when you turn on that current, it's going to cause a force on this that will force that little pin into the location that you want. We saw this, I don't know if you remember, for the circuit breaker. Remember we had two different types of circuit switches for the circuit breaker. We had one that was based on the heating of a bimetallic strip, and when you ran a current through it, the bimetallic strip turned one way or the other, turning off the switch if you got too much current. The other was a solenoid switch that looks like this, where you have this little pin that sits inside of a solenoid coil, and when it gets too much current, it engages that pin and turns off the circuit. Which I think that's the more common way, this electromagnetic switch. You have this in your car too. You ever worked on your car? You know your starter. It has a solenoid on it. When you turn your ignition switch, it engages that solenoid switch, which kick-starts your starter and starts your car. So it's a way of engaging a mechanical switch from a distance from the inside of your car. Let's see, I have a little video about the solenoid switch. It has this really cool guy on it, and he's British, but British guys. Anyway, let's see. Example. I don't know, look around and see where you see solenoid switches. Anytime you have a mechanical switch that operates by an electrical signal, it's probably going to be a solenoid switch. Okay, I think that's it for that chapter. I think we have a few more clicker questions. Is that right for chapter 5? Did we finish the concept test on the back? You recall? don't remember. We might have. You'll recall. Anybody? Yeah. What's that? 5.10.
Yeah, I think that's chapter 6. That's not the number.
Yeah. I think so. We did this one? Okay. Okay, yeah, so we finished that one. Yeah, the next ones that are not numbered, that's the next 2 chapters. Okay. Any questions about this chapter? Like I said, we're going to pick up on the next exam with going past the QBB. So you'll still see some right-hand rule, and you'll still see some probability, you'll still see a cross product, but as related to the IL cross B. Remember, those are a little bit different because you have to determine what is the L vector. Like we did in class, find the X and Y components of the L vector. Okay? Various other applications of the right-hand rule, magnetic field along a straight wire, the force between wires, all that stuff. Okay? Feel comfortable with it? Go through the homework next couple of days. If you have questions, we can work out in class. But you should be working through the homework on this chapter. Begin looking at some old exams as well. Let's see. Let's go on to chapter 6. We're going to look at induction and inductance. That is, how do we create a current with a magnetic field? We found previously that a current causes a magnetic field. Remember, like for example, we had well, just like in the solenoid switch, that when we have a current that flows through a piece of wire, then it generates a magnetic field in that direction. And then also a current is caused by an electric field. We can return back to our capacitor plates, right? That if I have a positively charged plate, a negatively charged plate, that I have an electric field in this direction, and a positive particle is going to move along those electric field lines. So when we think about, we don't really talk about current in this way, but it's very much true that when we have a current flowing through a wire, the reason it's flowing through a wire is because we have this electric field that's set up within that wire. So a current causes a magnetic field, and then also a current is caused by an electric field. And we have this law called the Law of Induction. It says a magnetic field can induce or cause an electric field. And if a magnetic field can produce an electric field, that means it can also produce a current. I have a couple of experiments that Faraday did in the late 19th century, sort of the late 1800s, like 1880s, 1890s, I think. The first thing that he did is that he took an ammeter. Right, an ammeter measures the force on the wire, just like the way we define what the amp is. It uses that same standard. So it measures the force on the wire to determine the current. So he took an ammeter and he hooked it up, and he made a setup like this, where he had a loop of wire, just like this. It was hooked up to an ammeter, and then he took a magnet, North Pole, South Pole, and he would move it in and out of this coil. And what he found was that that caused a current to flow. So he would move a magnet in a coil of wire, and measure the magnetic field. I'll show you what he did here in just a second. I'll show you how he did that. Then he also did, and he found a few things. First, he found that current occurs when the loop or the magnet moves. All right, so he found that either you can move the magnet or you can move the loop back and forth. And in fact, in generators, what do we do? In your electric generators that we use at hurricane season, what do we move? Do we move the magnet or do we move the loop? You ever taken apart a generator? Right, you move the loop. You don't move the magnet. The magnet's really heavy. It's heavier than the loop of wire, so it's just easier to move the loop around. And in general, in generators of larger types, that's what happens. You move the loop. So it doesn't matter if you move the loop or the magnet. Either will produce a current. The second thing that he found is that a greater current occurs when it moves quickly. All right, so if you move the loop really fast, then it'll produce a greater current. And then the third thing that he found was that the direction of the current depended on the motion of the magnet. All right. Let me show you his other experiment that he did. It's less implications, and then we'll show you back in the back. I brought some stuff I'll show you. So he set up another experiment that looked like this. He took the first setup where he had the ammeter. He had a coil of wire like this. It was just a little circuit. And then he had another coil of wire. They weren't touching, but this coil of wire was hooked up to a power supply like this. And what he found was that when you turn on this circuit, that it causes a current in this circuit. So turning on the battery causes a current in the ammeter. This is the idea that we have behind transformers. When we have those step-up and step-down transformers, and we'll get into that in this chapter, how that works actually. But it's pretty remarkable that you can cause a current in this circuit without actually doing anything. You're not touching this circuit at all. You're just turning on a current in this circuit. All right? So when I turn on this circuit, it creates a current in this circuit. And much of our electrical system is based on this idea. Let's see, I've got galvanometer and stuff today, so let's look at it. I'll try to just come over here. It'll be easier for you to see. I'll show you the little motor before. I'll show you that. Come on over first. Can't see. You won't be able to see the numbers. Just a little closer. All right, so this is the first experiment that he had. This is just a loop of wire. It connects here and then it just runs around here and then it comes back out here. So it's just like that first one that he had. We had the loop of wire and then he had a very sensitive ammeter. Y'all use these in labs, I think, right? These are galvanometers, but they're really just ammeters. They're just very sensitive ammeters. We call it a galvanometer because it doesn't have that shunt resistor in it. Right? You know, talk about shunt resistors in the ammeter. The ammeter has big or small resistance. You remember that shunt? Is it big or small? It's really small, right? So an ammeter is just a galvanometer with a shunt resistor. So anyway, this measures very sensitively currents. It has 3 buttons on it to change different sensitivities. Right? Now use the buttons. Now this is the magnet, south pole, north pole. Notice when I put this in here, I get a little bit of wiggle on the needle. You'll see that. I'm going to go up sensitivity there. It's moving. I've just made it more sensitive to scale. I'll go up here. And now as I move the magnet, I get current. So a couple of things that he found. First of all, that you just get current when you move this magnet. Or So I can either move the magnet or I can move the loop of wire like that. And also that if I move the current, I move the magnet more quickly, you'll get more current. So watch, I'll pull it out really fast and it jumps up. But if I just do it really slowly, I don't get much current at all. If I do it really quickly, I get more current. Okay. And then the third thing we found was that the direction of the current was dependent upon the direction of the magnet moving. So we talked about, we'll get into alternating current, where you have plus current and negative current. That's just the direction that it goes. It refers to the direction that it goes. So if it's going in this direction, it's either positive or minus. If it's going in this direction, it's the opposite of that. The galvanometer, unlike your ammeter, will measure positive and negative current. So here, the current is going in the negative direction, and here is going in the positive direction. So those are the three things that Faraday found. That first, that just current occurs when this happens. That greater current occurs when I move it really quickly, and then it changes direction. Something else for here, we can also do this with an electromagnet. So this is just another coil of wire. Y'all do this, Lynn? You don't do it, do you? Nobody's doing that. Which is unfortunate, but we are doing like all optics now, right? We don't do this class anymore. Okay, so this is just, it's an electromagnet, but you get the same effect. It's kind of weak, unfortunately. So here I have a current. It's just sort of barely wiggling. I don't get nearly as strong a magnet because it's my power supply. You ever see a little needle wiggling a little bit? Okay. Oh wait, no. Let me show you this first, because this is pretty cool. So what we're getting into is that anytime you have a changing magnetic field, it will induce an electric field. And if you have an electric field, that will induce a current. So this is just a little cutaway of a motor. I think this was from our weed whacker or whatever. And this turns here, right? You have a gasoline motor, you put gas into the piston, it pushes the piston down, which causes this to turn. This is a two-stroke motor, so there's two strokes of fuel. But of interest here are these two little magnets right here. So you have two magnets, and as they rotate around, you can actually feel them catch. How fast around you can try it. But they sort of catch here because they're causing the magnetic field here to change, and they're inducing an electric field in these metal plates, which connect, I forget what this is called. I guess it's not right, Mr. No, you might know what this is called. All right, anyways. Yeah, okay, yeah, so is that what it's called in a two-stroke motor like this too? Okay, so anyway, this thing takes that current and sends it to a spark plug, which then goes back to your piston. So you have this little electric generator in your motor, and this isn't all motors. You just put magnets in the flywheel, I guess, and then that causes a change in the magnetic field as that magnet spins around, which generates an electric field here. It's a pretty clever idea, actually. I don't know if you thought of it, but it's a good idea. I guess maybe Faraday. Okay, let's see. I'll pass this around. Those experiments might not seem very exotic to you, but they really change the way that we live because they make our electrical system possible. And we'll look at his law of induction and how we use that to generate an electric field. And then also, as I said before, that second experiment, this one right here, and how we use that in transformers, which make our use of alternating current possible, and that allow us to transmit electricity over very large distances. All right, let's look at the law of induction. Refined, what does that mean? I don't know why I put refined there. Maybe it's for more refined audiences like yourself. I don't know why it's called it. It shouldn't be called refined. Must have been a note I made to myself. All right, an EMF is induced when the number of magnetic field lines that pass through the loop is changing. I think this is actually how Faraday noted this law of induction. Remember, Faraday also defined these electric field lines, and he also defined what magnetic field lines. So he very much thought about these fields in terms of these field lines and as we draw them. So if our number of B field lines is changing, that just means that our magnetic field is changing. It's when we move that magnet back and forth in the coil of wire. So to find the EMF, one first has to be able to calculate the magnetic flux. Listen, we've done flux before. We did it with electric flux. We did it with gravitational fields. And so now we're going to do it again with magnetic fields. So this should be somewhat familiar to you, but instead of gravitational or electric fields, we're now dealing with magnetic fields. But the process is still the same. So our magnetic flux, or capital phi, of our magnetic field is equal to the integral of B dot dA and if you recall, our vector here, dA, is a vector that's perpendicular to whatever the area that we're looking at. So remember how we did the Gaussian surfaces and we defined the vector area dA, like with the cube, for example. So if this was our face, then our vector dA was coming out perpendicular to it. We'll have a similar thing here. So therefore, in order to have any flux, your magnetic field will have to be moving in a direction that's perpendicular to our area. If it's moving in a direction that's parallel to our area, our dot product goes away. Because remember, our dot product takes two vectors that are in the same direction and takes the product of them. If they're perpendicular to one another, then they're not going to have any dot product at all. Do you recall dot product? Okay, so this is how we define our magnetic flux. Here, dA is a vector that is perpendicular to the area. So for example, if I have an area like that, my vector dA will look like that. All right. If the B field is perpendicular to the loop, this symbol just means perpendicular at 90 degrees to the loop. So imagine that I have a loop that looks like this, a loop of wire, then I have a magnetic field that is perpendicular to it. This is my magnetic field. In that case, my angle theta is equal to 0 degrees because my magnetic field and my area vector are both in the same direction. Goodness bless you. Actually, in this picture, the way I've drawn it, it depends what your area vector is. It could either be 0 or 180 degrees, but still our dot product will have a magnitude equal to 1. Right? It's not going to go away. So here our angle we'll just say is 0 degrees. So B dot dA is going to equal to B times the area. And we're dealing with a differential element in A, but we can just think of it in this case right now as just what is the area of this dA. So B dot dA is going to be equal to B times dA times the cosine of 0 degrees. And of course, cosine of 0 degrees is just 1. So this just simplifies to B and dA. And then our flux is going to be equal to the integral of B dA, which is going to be, in this case, if our area is equal to A, is just going to be B times A. Or rather, if our magnetic field is constant and it doesn't change over the entire area, it's always the same, then I can pull the B out and I just get the integral of dA, which is just A. Let me put that in words right quick. So if B does not depend upon the area dA, and if that's the case, then you get B integral of dA, which is just equal to BA. Okay, this is just like what we've done before with fluxes, when we did it for gravitational fields and for electric fields. Faraday's law of induction further says that the EMF is equal to the rate at which this flux changes. And then also the EMF, which we call the script E, opposes the change of the B flux, the magnetic field flux. All right, so our Faraday's law then is going to be EMF. Be careful, I would differentiate here between E and script E, because remember, capital E is going to be electric field, but script E is going to be our EMF or our voltage. If you want to use a V when I use a script E, that's fine, but I'm going to use a script E because that's sort of standard. All right, so our EMF is minus d phi dt. This is our flux, how our flux changes with time. So the EMF is equal to the rate at which the flux changes. That's this, d phi dt. That's the rate at which it changes. And then further, the EMF opposes the change of the B flux. That's where this negative comes from. So the EMF is going to oppose the change of the B flux. And then further, if we have N turns of wire, we'll get that E is equal to negative N d phi dt. So just like what we've seen before, if I add 2 turns of wire, it's going to double my EMF. We saw that with the loop of wire with our magnetic field. If we had multiple turns of wire, then we'll just have that many times more magnetic field. All right. So there are 3 ways to change the flux with time. We talked about this a little bit. One way is you can change the magnitude of B within the coil. All right, so if we think about our coil and it has our magnetic field in it, if we make this magnetic field get smaller, bigger, smaller, and bigger, smaller, and bigger, only in magnitude, but we keep it in the same direction, then we're going to generate a current within that loop. So one way that you can do this is just make the magnetic field change with time. You can do that with an electromagnet. Excuse me, kind of like when we had the electromagnet back there. If you just change the amount of current going through the electromagnet, it'll change the magnitude of the magnetic field, which will generate a current. So you can change the magnitude. The second way is you can change the area of the coil in the B field. All right, so if I think about this example again, remember my phi here is equal to B dot dA. So the first thing that I can do is I can change the magnetic field. The second thing that I can do is I can change the area. So if I have this loop of wire in this magnetic field, if I make it bigger, smaller, then that also generates a current. All right? I can change the magnitude of the magnetic field, but I can also change the area and that might not appear like that might not occur to you that if you just change the size of this loop, that will generate a magnetic field as well. What's the third way? It can also generate a magnetic field in a third way. Now our flux, remember when our flux changes, when we change this value, then we get a current, or we get an EMF. So I can change the magnitude of this, I can change the magnitude of this. What's another way that I can get an EMF that's induced? And this is the most common way. What else can I change in this expression? The direction. Yes, you can change the direction. So remember, I can write this dot product as equal to BA cosine theta. So the other way that I can do this is by changing the direction, or changing the angle theta between the magnetic field and the area vector. So I can change the angle theta. All right, so right here, the angle theta is, say, 0 degrees. But I can change that angle theta by doing what to this scenario? To this, I rotate the thing, right? And that's the most common way that we induce a current. So we change the angle theta by rotating the coil. As I said, that was groundbreaking, that if you rotated the coil, that you could actually generate a current and change the way that we live, like for a century or more. It was groundbreaking. Let's look at a graph. So let's say that I have a graph here of the magnetic field versus time. And the magnetic field goes along like that, and then it increases, and then it's constant, and then it decreases. I'm going to break this into segments. We'll call this segment A. I'll call this segment B, where it does this thing. I'll call this segment C. That's this section right here. And then we'll have D and E over here. I want you to tell me where is, on this graph, where is the EMF the smallest? Is it A? Is it C? Is it D? Is it D and E? Or is it A and C? Where is the EMF the smallest on this graph? Is it A, C, D, D and E, or A and C? Be careful with your letters. They don't all match up. A is the one that matches up. Where is the EMF the smallest? We'll assume that everything else remains constant. We're just looking at the magnetic field changing. So the area and the angle will remain constant. But where is the E the smallest? All right, so a few more seconds. Let's stop at about 1 minute. Yeah, we'll stop at 105, 105. Okay. E is the right answer. Let's look at A. And what was the other answer you put? D, D, and E. A is sort of the next best, or is sort of the next most favorite answer. You probably put A because the magnetic field is really small here. But remember that the EMF is not dependent upon the magnitude of the magnetic field, but the EMF is dependent upon, well, it's negative d phi dt. But remember that phi is equal to b dot dA, the integral of b dot dA. So what we're looking at here is not the magnitude of the magnetic field, but how that changes with time. So just because you have a low magnetic field, that doesn't necessarily mean that you have a low current. And in fact, in this case, since it's not changing at all here, then I have zero current. So this is one of the lowest currents. But also here where I have a big magnetic field, it's not changing, so I also have no current at all there. Where is it biggest, the EMF? The EMF here is biggest where it changes the most. So which of these sections, A, B, C, D, or E, is the EMF the biggest? What do y'all think? I have a D and a B. We're not looking at that. I'm not doing B, yeah. So B is where it's the biggest. The reason that it's the biggest here is they're going to change the most. Doesn't matter about the magnitude of your magnetic field. It only matters about how quickly it's changing. All right. Let's do this quick example, and I'll let y'all out with the solenoid and how the solenoid works on the next page. We'll see some more questions like this, so don't sweat it if you're not getting it just yet. Solenoid has 1.5 amps and 220 turns per centimeter. There's its diameter. You place another coil inside it, and it has that diameter. The current in the solenoid is decreased to 0 amps over 25 meters per second, over 25 milliseconds. What is the EMF in the coil? All right, so there is a changing flux in the coil C, that's in this coil, the one that you put inside of it. So I have one coil here, and then I have another coil that sits inside of it, just like the device that we had over there, where I have one coil that goes into another coil. And this red coil here is the coil C, the one inside of it. So there is a changing magnetic flux in the coil C because the current in the big coil is decreasing. All right, so I start out with a current, what was it, 1.5 amps here, and then over time I gradually let it decrease. So that causes your flux to change. I know that my EMF is equal to negative N dphi dt. Actually, you know, before we go any further, why don't we stop there? That's sort of a good place to stop. And we'll pick back up with this question on Friday. I would go ahead and start that homework. You could probably go ahead and start looking at some of it. And y'all stay safe today. How's it looking, the weather?
Not very well.
Yeah, I mean,
It was going north of us, but now we're in the yellow and red.
yeah.
There was a tornado. What? I'm on the way to school, my phone's going off.
All right. Well, listen, start that homework, okay? Go ahead and start it this week if you can. Do the first couple problems at least. Have a great day.